So welcome back. This is part 2 of lecture 5 and we are going to talk about bagging. Okay? So it's the introduction to bagging. These are the references that we are going to look at, and again all of them are available on our Google Drive folder. Okay? So what bagging means is basically an acronym to bootstrap aggregating. Okay? And it was introduced by Leo Breiman in a machine learning paper in 1996. And the idea is to reduce the variance of a predictor, but I will show you that it works in a broader scenario, a broader framework. Okay, so let's consider a regression setup where data is collected. That's this ZT, that's going to be Y, the dependent variable, and X, our covariates. We have T observations, okay? And let's define a statistic that we call theta hat of X, that will be a function of the data, of all the sample, function of the sample, so that's why we have here all the Z's, okay, evaluated at X, okay? And let's assume that this theta hat is an estimator of the condition expectation. So again, as in the previous block, our goal is to estimate this condition expectation, okay? And so what's the bagging algorithm? So we are going to construct a bootstrap sample of the data. So basically what we're going to do, we're going to take the data, the original data, and we are going to resample with replacement from the original data, okay? And then we are going to form a bootstrap sample that we are going to call Z star, okay? And for each bootstrap sample, we are going to compute our statistic, our predictor, theta hat. And now we're going to call it theta hat star. But look at here, our theta hat, the original theta hat of X, is a function of what? Z1 to ZT, the original sample, and it will be evaluated at X, okay? The theta star will be a function of the bootstrap sample, of this new sample that we sampled from the original data with replacement, okay? So we are going to estimate H, this function H, with the bootstrap sample, but we are going to evaluate it at the point X, okay? The bagged predictor will be the expected value, and here we use this notation E of E star. That means that we are going to take the expectation with respect to the bootstrap distribution, okay? And so that's the bootstrap estimator. It may look quite obscure right now why we are doing that. I promise you that this will become much clearer in a few slides, okay? So in practice, the expectation will be computed by Monte Carlo. So for each bootstrap simulation, and we are going to repeat this resampling technique capital B times. So we go to the original data set and we are going to sample with replacement, okay? For each bootstrap sample, we compute the statistic of interest that we are going to call theta star hat J, because it means that it's the Jth bootstrap sample, and it's going to be computed as it's shown on the slide, okay? And in the end, what we are going to take, we are going to take just the sample average. We are just going to take the average of the bootstrap statistics, okay? So that's our final estimator. Okay? And what I will show you that can be drastic variance reduction if the predictor is unstable. And this is a key thing. Okay? what's the intuition behind that? Okay? Imagine that you have variables with the same variance, okay? So let's define a variable x, which is normal 0 sigma square. Okay? And let's say that xy will be 0 sigma square. Question for you, what's the variance of 1 over b okay, xy, assuming that xy are all IID. So this will be the 1b squared, okay, the sum of the variance of xy, so this will be 1b squared b sigma square. So this is 1 over b sigma square. So as b diverges, you reduce the variance. Okay. Of course, it's a very hypothetical setup. So I'm going to show you when this fact will kick in, and this variance reduction will be very useful when you have some kind of unstable statistic. And I'm going to define what I mean by unstable statistic. Okay. So before doing that, let's recall what the bootstrap is. Okay. So let's say that we have the original data set. We have like 10 observations. Okay. That's t here is equal to 10. So you take your original data set. That's the pink squares that you have on your screen. Okay. So what I'm going to do, I'm going to sample with replacement to construct another sample with the same number of observations. Okay. So we are going to construct another sample with t observations. But now it's important to sample with replacement, because if we sample without replacement, we are going to end up with the same sample, just reshuffling the observations. Okay, so that's why it's important to sample with replacement. So let's say that the first bootstrap sample we got x2, x8, x4, x6, x2 again, x7, x3, x7, x7, x8. That's our first bootstrap sample. Then we are going to come here and we are going to compute the statistic with these 10 observations. That will be our theta star hat of bootstrap sample 1. We are going to repeat these b times. For the second bootstrap sample, we have theta star 2, the third one, the fourth. Here we have 5 bootstrap samples, and we have here like 5 different values of our statistic. What we are going to do next, take the average. That's our final estimate. What's this statistic? It can be any statistic. In our case here, it's a forecast, it's a prediction. Okay? And we want to reduce the mean squared error of this prediction. That's the goal. Okay? But this can be any statistic that you wish to compute in each bootstrap sample. Okay? So what's an unstable predictor? So let's define what a stable predictor is. So let's take our statistic, our theta hat. This is called a stable at x if it converges to a fixed value theta without the hat plus some term that vanishes as t goes to infinity. Okay? Bear in mind that this is different from consistency, because I'm not saying that this theta of x, this fixed value that it converges, is the true value of that statistic. The population value can be any value. So any estimate will be stable even if it's biased, but if it converges to somewhere. Okay? So if it converges to somewhere, we are in a good shape. We have a stable predictor. Unstable predictor is when this condition does not hold. Okay. So as I mentioned, it's different from consistency. Theta x is just a stable limit, not necessarily the parameter of interest, not the true population parameter. Okay. And basically, subset model selection creates unstable predictors. Okay? So let's see an example. Very simple example, okay, where our statistic, we are just going to compare the sample average. We have a sample of y's, t observations. We take the average, the sample average, that's y bar. Okay, that's defined on the slide. And our statistic, theta hat, evaluated at the point x, we are going to be an indicator function, and it will be equal to 1 if the sample average is less or equal x. And it will be 0 otherwise. Okay? So it's a kind of threshold. It's a step function. Okay? Pretty simple, right? And so we know from the central limit theorem for, we are assuming here that the y's are ID, okay? So plain vanilla central limit theorem, we know that square root t, y bar minus mu, will converge in distribution to a Gaussian random variable that's 0 mean and variance sigma square, okay? And which sigma square is just the variance of the y's. Okay? This is kind of statistics 101. Okay? No, nothing new here. Okay? We know that. All right, so now let's do the following. Let's take the x like this threshold here, where if y bar is below that x, the function will be 1. If it's larger than x, it will be 0. Okay? And let's take an x in the neighborhood of u. Why is that? Because we know that y bar minus mu has mean 0, asymptotically. Okay? So this is kind of around 0. So let's define our threshold x as a xt of c, c is a constant, that will be mu, the mean, okay, plus a term that depends on 1 over square root t and sigma. So basically, what we are comparing, that you see the point here, the instability. If the true mean is mu, you know that asymptotically y hat will eventually converge to mu, okay? But it can be slightly larger or slightly smaller. Only when t gets to the limit is when we have y bar just over mu. So we are looking at the neighborhood, close neighborhood of this limiting point, okay? So small discrepancies from mu will get you a theta that will be 0 or 1, okay? So we can say that theta evaluated at this new threshold, okay, is approximately distributed as an indicator function of a Gaussian random variable, standard Gaussian random variable, see if it's z is less than c. Why? Simple way to see that, because we are comparing a variable that in the limit will have this convergence rate, and we are looking to the probability of this being larger or less than c, and you're going to see that's exactly the probability of a random normal, a Gaussian random variable, standard Gaussian variable will be less or equal than c. Okay, just taking this result here with the definition of our xt of c and the definition of theta, you get to this result, okay? So with that, we can take the expected value of that. So what's the expected value of theta? Is just the probability of z less than c, which will be the cumulative distribution function of a Gaussian random variable evaluated at c. Okay? What's the variance? Okay, that's the variance. Remember that theta is 0, 1, so it's a binary variable, right? A Bernoulli variable. So the variance of theta is just the probability, the average, 1 minus the average. So it will be phi of c times 1 minus phi of c. So that's the limit. So that's the variance. So basically here, what we say that this is in the limit when t goes to infinity. So the variance of our statistic is not vanishing. It's not going to 0. So basically, this estimator, the theta hat evaluated at this point, that's really near the cutoff, is unstable. Okay? So let's see how bagging can help us here. Okay, so the predictor is unstable. So now let's think about averaging over bootstrap. So our bootstrap estimator, okay, will be the expected value of this indicator function, but now we have the bootstrap average. We are going to compare the bootstrap average with our threshold value. Okay, so this will be the expected value of indicator function square root t y bar star minus y bar divided by sigma less than square root t xt minus y bar divided by sigma. So basically what we did, we subtracted y bar from both sides here. We divided by sigma and we multiplied both sides by square root t. Okay? So basically here we have a normal approximation. So if the bootstrap works, okay, we can show that this expected value is nothing else than the cumulative distribution of a standard normal variable evaluated at square root t times xt, our threshold value, minus y bar plus a term that vanishes. And from the central limit theorem, okay, we know that convergence in the distribution to this quantity here. So this is just the cumulative distribution of a normal evaluated at c minus a random term that's a normal 0, 1. Okay? And this is just application of the CLT. So basically what we are doing, that's our estimator, right? So compare here. The original estimator is a step function. Okay? And depending if your value of your argument is here or there, you have completely different outcomes. If it's here, it's too close to the threshold, but it's above the threshold. So theta is 0. Here, it's also close to the threshold, but it's below, so it's 1. So anything that's around the threshold is very unstable. You can go from one side or the other. Okay? But on the other hand, what the bagging is doing, the bagging is moving the decision function, okay, around the threshold. So instead of having a sharp decision, a sharp threshold, we are including a smooth threshold. Okay? So let's take the value of xt at 0. Okay? So let's make c equals to 0. So we have that our estimator will converge to a uniform random variable. So we can compute the average and the mean of a random variable, a uniform random variable. So we have that the average is 1/2, 1/2. The variance is 1/12. Okay. So bagging is asymptotically unbiased. Okay, if we take the expected value of this function, okay, so it's just 1/2. Okay, but the asymptotic variance will be reduced by a factor of 3. Because why is that? Because the original estimator will have, remember the first slide, that will be the variance of the original estimator. Okay, so this will be 1/2 times 1/2, 1/4, but the bagging estimator gives us 1/12, 3 times less. Okay. So when we are around the threshold, or the region where we have instability, bagging will yield a major variance reduction. Okay? So that's what we can see in the plot. So the plot that's most to the left is the variance of the estimator, okay, and the dashed line is the bagged predictor, the dotted line, and the bold line is the original one. So you see when your threshold, when C the C value is close to 0, so you are exactly on the spot, on the point where you have the cutoff on your function, you have a major variance reduction. See, major. This reduction decreases as you go further away, and then bagging is doing nothing. But around the threshold, major one. Of course, this comes to a cost, because then, like shrinkage, you are reducing the variance, but to reduce the variance, you have to increase the bias. So of course, exactly at 0, the bias is 0, but that you have some bias, and then again, this bias, you have bias here, but this bias will eventually vanishes. But the point is that in terms of mean squared error, asymptotic mean squared error, you have massive reductions. Okay, so this is really an important thing and very nice of bagging. So the idea is to use bagging to reduce the variance of unstable estimator. What can be an unstable estimator in our setup? Well, let's say selecting a regressor. In a regression, if your regressor is like barely significant, depending on the sample, you can put the regressor in the model or not in the model. Remember that Lasso makes mistakes when you have regressors that scales like 1/√T. So smallish coefficients will eventually be set to 0. So if it's a little bit larger, it can be included in the model. So maybe bagging combined with Lasso can help in these situations. Maybe bagging with t-tests can help. So there are many ways where bagging can help us. Okay, we can do the same thing with, of course, with a more interesting model than a single threshold model. We can look at regressions, okay, and where the idea is to decide if we are going to include a variable x in the model or not. So in this case, I'm going to do the analysis all based on IID and orthogonal covariates. So the covariates are orthogonal, everything is IID, okay. And basically, we have the procedure as follows. We run the regression, we compute a t-test to test the hypothesis that the kth variable has a coefficient in the population that equals to 0. If we do not reject the null, we remove that covariate. If we reject the null, we keep it, okay? And we do this in a sequence to select the model. If the variables are either the coefficients are too big or exactly equal to 0, so if we can like split these two groups, then this procedure eventually will work. However, if you have regressors associated with smallish coefficients, this procedure will fail completely, okay? Because you may make mistakes because you are very close to the threshold with the decision rule to keep the regressor in the model or outside the model, okay? So the idea is to use like bagging. So our statistic will say, our prediction, we are going to say that we are going to keep only variables where the coefficient exceeds a certain threshold. And of course, this threshold is related to the significance level of the test, okay? And depends, of course, of the standard error, but basically that's the decision rule, okay? And usually the decision rule, see, it will depend on the critical value of a t-distribution, on the residual standard deviation, and the empirical variance of here there is a typo, it's square, okay, of the regressors, okay? So basically, this is innocuous. Here is this horrible theorem, but basically what these authors, they show that the bagging estimator will converge to some place. It's an ugly distribution, but the important thing that what bagging will do is that we have a hard threshold that say that if the coefficients between these bounds, you set them to 0, otherwise your prediction will be just a linear model. What bagging will do is that it's going to smooth your decision surface, okay? And more important is that picture that for a smallish coefficient, you can have a big reduction in variance. You can have also a reduction in the bias and on the MSE, okay, for linear regressions. So if you want to do model selection in linear regressions with t-tests, you may consider, if your interest is in prediction, okay, you may consider doing bagging. So the question for you guys is that how can bagging and penalized regression can join forces? Do you see any way where these two methods can join forces, or when one is preferred to the other? Okay, so that's also a question to you. All right, so how can we run this bagging in a time series framework? Okay, let's assume that we want to we have a model that's like that. We want to forecast y h steps ahead. We have a vector of variables xt plus an error term. Okay, how we should do? We should organize the data like yt plus h xt, okay, in a matrix V of dimension t minus h p, okay, and we are going to draw bootstrap samples from this matrix, constructing our bootstrap sample here, okay. For each bootstrap sample, we are going to estimate this regression, select the coefficients that are significant, throw away the others, and estimate the coefficients, and use these coefficients to make our forecasts. So we are going to do it for each bootstrap sample, okay? So in the end, we are going to have forecasts computed for each based on the estimates of each bootstrap sample. So what we do in the end, we average them, okay? And this can be shown to have massive variance reductions. Okay. The authors have this paper on JASA, and basically what they show here is that the bagging estimators this is predicted mean squared error, overperform the other methods. Okay? That they are using basically unrestricted forecasts or principal component forecasts, and doing some also doing some pre-test, but basically bagging helps. Okay, but I think the big question is that choosing between bagging and lasso or combining both, and I'm going to show you an application where bagging, I can show that bagging can be more general than just improving on t-tests. Okay, so that's our second block. See you on the third block. Thank you.